So hello, welcome everyone. This is the ADDITOOL webinar. This is the last webinar of the ADDITOOL project. It's going to be a webinar about conformal cooling channels in plastics injection molds. And we are going to have basically two parts of this presentation. The first part is about application cases of this technology in injection molds. This presentation, this part of the presentation will be held by Luis Santos, which is one of the people involved in Aerofio company, which produces molds and inserts using the additive technology, technologies. And on the second part, we will be having Nelson Ferreira, which is going to be telling us about new developments in the future generation of automatic cooling channels for all these applications as well. So, but before that, I'm going to give the word to Professor Artur Mateus, which is going to be introducing the topic of conformal cooling channels in plastics injection molds. Okay, so please, Artur.
Okay. Good morning, and thank you to be here here in the morning. The conformal cooling channels subject, okay, is one of the main important topics in metal additive manufacturing for injection molding. If you look, it's really, I think, the unique advantage, perhaps one of the unique, but perhaps the close to the unique advantage that additive manufacturing give to injection molding or tooling for injection molding. If you look back in 1990s, we have not direct additive manufacturing by using metal, but we have rapid tooling. That time used the words rapid tooling for making molds with conformal cooling, but by using of resins with fillers, metallic fillers. And that time also the cooling time, it was a challenge. Nowadays, for instance, in Marinha Grande, we have perhaps between 250 to 300 small and medium companies that works making molds for plastics. And we have a lot of tooling companies that already have machines producing inserts for injection molding. And the main objective is really to increase the performance of the cooling and let's say cooling and heating molds for getting better parts and also decrease the cycle of each injection cycle. So conformal cooling channels are an important, very important topic here in our industry, and according to that, for instance, we have here Luis Santos for Aerofio that they are betting a lot on this area since perhaps 50 years ago. And one of the important things is to, how can I say, design the cooling channels. That is a challenge because the cooling channels could be very complex, and nowadays we need to design it manually or close to manually by using CAD software. So, and this give us the second topic. Second topic, it was presented by Nelson, and here in the CDRSP we are developing some algorithms to design automatically with some rules the cooling channels. So it was what I want to tell, and the important thing is and I want to underline the importance of the conformal cooling channels, the application, and also the importance of the automatic generation of the conformal cooling channels in our region for our companies. And okay, we could start now, I think, with Luis giving us a practical, some practical applications of that. Thank you very much.
Okay.
Yes. Yes.
First of all, thank you very much for the kind invitation to be here today and present what we are doing. And second, for the kind introduction too. And I hope you will enjoy as much as I do. I will be talking about conformal cooling channels, in this case by Aerofio, and what we do at our additive manufacturing unit. A little bit of Aerofio's history, our additive manufacturing unit, what is conformal cooling channels, the influence of them in the plastic injection process, a little bit of it, some case studies with simulation, and a portfolio of build jobs that have been done and what is possible to do today, I would say, or better, what we are doing. Aerofio's history. Everything started by the end of the Mr. Novo, Manuel Novo, that's on the photo, in 1990. So we are talking about mold making, tool making division. We are talking about injection molds, production and facilities, and a lot of knowledge that has been developed since that. In 2000, Mr. Novo sees the need for a plastic divisions where he can test the molds, the produced molds, produced tools, and validate the plastic parts. So he founded Aerofio Atlântico, and today Aerofio Atlântico, it runs not even tests, but injection productions of plastic parts. In 2011, we started with the additive manufacturing at the time, laser powder bed fusion system with the concept laser machine M3 linear machine. So right now we have 12 years since we have working on the with metal powder bed fusion systems. 2013, Mr. Novo started a new facility, a new plant at Batalha with 17,000 square meters. And 2018, we bought the second additive manufacturing machine, laser powder bed fusion system 2, an M2 machine, faster technology and more reliable than the previous one. And in 2020, we built a new facility, a new building for the additive manufacturing unit, a new division that are dedicated just to build most of it inserts with conformal cooling for the tool applications. And in 2021, it was bought a new machine, M-line machine, a bigger system with 4 lasers. So right now we have 3 machines. Our additive manufacturing unit, what we do, we right now are focused on AM service providers. So we are providing and supplying our competition, our partners with tool inserts with conformal cooling. We are doing modifications, repair of damaged components, and then some prototypes or concepts for automotive, aeronautics, and some contract manufacturing for a small serial productions or first tryouts, we can say, for testing. We are always doing some research, parameters optimization, looking for solutions like we have the porous steel that we are using for venting, for ejection of the plastic parts, for example, for lubrication or greasing, and to do vacuum according to the needs. And that's some things that we are exploring and creating new solutions for the needs of every day, I would say. There is a small video from our M-line machine. It's a system that it's a laser powder bed fusion system too. It has a build plate of 500 per 500 millimeters with a z-axis of 500 millimeters. So we can, like this, we can build pretty big parts on for this kind of systems. It's a quad laser system. And here we have some build job of real inserts. Okay. Now we have a new layer of powder that was being coating, and it will continue to melt the steel powder. And it will repeat the process until finish the parts layer by layer. Now, our main subject, what is conformal cooling channels? Small definition, what we call conformal channels are two channels that are close contouring to geometry of interest. In our situation, it's molding surface, reproducing, conforming its geometric features as perfect as possible. Conformal channels are used to achieve the most uniform, homogeneous temperature possible in the molding surface. That's one of the goals, the best goal that we need, that we want. Being of the most importance for the plastic part, it will take impact on the quality of the part and the stability and the reproducibility of the injection process. They are used most of the times just to cool down the plastic during the injection cycle, but they can also be used, like it was previously said, to do heat and cooling, depending on the needs of the injection process and the technology available. Due to the complex geometry of the plastic parts and by consequence of the mold of the tool inserts, the conformal cooling channels can't be easily created by conventional technologies most of the times. Like this, they are designed on CAD systems and printed using the additive manufacturing technologies. In our case, laser powder bed fusion systems. The parts are printed according to its final application with special developed set of parameters, taking care to the finishing requirements, porosity, textures, and polishing grades. The most used cross sections of the conformal cooling channels can be seen are round ones, ellipse, like rectangular, triangular, and teardrop shape are the most common or better, the most used by us, I would say. A few examples of parts that have been developed and done and that are working on the real molds and real tools. Here we have a jiggle pin, and from left side we have the cooling design, how it looks inside the part, and on the right some photos of a similar part of a real part, and on the right corner we have a part that was coated with DLC coating. Can talk about the influence of the conformal cooling channels in the plastic injection process. Are some topics, could be more if we go deeper, but these are the main focus. So one of the main issues is the cost. The cost of the plastic part, it's depending of the injection cycle time. So this is one of the items that will influence the cost of the part, and it could be reduced by decreasing the cooling time. So this is one of the goals that impacts directly on the productivity and the cost itself. We can have other issues related to the quality of the part. For example, parts that are out of specification. For example, out of tolerance, general dimensions could changes according to the temperature of the plastic when injected, or better, when ejected. Okay, if the plastic is ejected too warm or too cold, it will even move, warp, distortions even after the ejection. It could happen, and this could be avoided or reduced by the conformal cooling channels. The warpage could be reduced or even influenced. Sometimes on the everyday practice, they change the temperatures of the cooling channels to induce warpage on the positive effect. Voids, air traps during the filling and packing stage could be reduced or improved in conjunction with the other kind of systems, with fast heating and cooling. For example, we can use the porous steel to remove this kind of problems from the cavity. We could have poor mechanical or fatigue properties of the plastics parts, so it could be improved due to the decrease of the residual stress, improved welding lines during the injection, in conjunction to, for example, with fast heating and cooling systems. It will help on these ones. And the aesthetic problems that could be reduced or improved. For example, problems with non-uniform textures, non-uniform gloss finishings and polishings on the plastic part, sink marks due to the different contractions, due to the different thickness from the ribs. It could be reduced or completely eliminated from the plastic parts. We have some notes too regarding the conformal cooling, because there are some things that we should take care, or at least to think about. Most of the times the cooling is done with water. This water could lead to rust. Of course, we could use stainless steels, and we have them and we are using them, but sometimes it's easiest just to use what the customer needs. So sometimes when you use water, could lead to rust, and it should be treated accordingly to avoid the rust, to avoid limestone, sludge, and or debris. Debris could be swarfs, for example, and that could be on the fluid itself or inside the conventional drilled channels arising from the finishing operations. And this is one aspect that we are talking about inserts that will be assembled on a steel structure, and that structure has drilled holes, and that drilled holes could be flushing swarfs or debris from them to inside the conformal cooling parts. And like we see, the complexity of the cooling channels, sometimes it's so high that they can damage the part, clog the pipe, and it will be a useful insert afterwards. So we recommend the use of filters, especially on small channels. For example, we have here an example of printed part that has very, very narrow cooling channels, but sometimes it must be done because it's the plastic part that demands and obliges us to go beyond the limits, I would say. So, like you can see on the middle, we have a 3 millimeter thickness steel part, and it's difficult to cool to create a cooling system on a part like this by conventional means. So we use additive manufacturing, and on the right side you can see an X-ray tomography from the real part and how it looks. So there are some, just a few simulation cases, just to show some difference between conventional cooling and the conformal cooling channels. This is an example of an insert. On the left, we have the conventional cooling. On the right, the conformal cooling channels. One of the ways could be designed on many different ways. And there we have some comparisons. Okay, we are comparing most of it. It's the change between the studies. It's related to materials. For the traditional cooling, we are using the high thermal conductivity alloys. Okay, it's just not the most common steels, but steels with high thermal conductivity. And we are talking about other copper-based alloy. Okay. There are not that many differences in our simulation, and the results are shown in the plastic part. Okay, this is a small corner of a full plastic part. That it's molded and formed by the previous insert. Like we see between the traditional cooling, there are more or less around 2 Celsius degrees difference, even with copper-based alloys. So on the right side, we have the conformal cooling channels. We are comparing two maraging steel alloys. One is stainless, the other don't. And the difference, the most important, it's that between the maraging alloys, we don't see big difference between the results, but between the conventional cooling and the conformal cooling channels, we can achieve bigger difference. So we have a decrease in temperatures around between 11 and 26%, depending on the regions that was assigned for the simulation. So we clearly have an improvement, even though the maraging steel alloys don't have high thermal conductivities. But the fact that the cooling channels are so close to the plastic make it really efficient. There is the case 2, another simulation. This tool has 3 printed parts, we could say. On the left side, we have a more complex one. And on the middle, we have the cooling channels that are inside that part. And on the right side, we have the remaining inserts that were printed. And here we can see the cooling channels used for the simulation of these parts. These are the simulation of the full cooling channels of the mold. Okay, and on the right side we have the printed versions, the file to print, and the printed versions of the parts and the inserts. And we achieved, we have reduced the cooling time in 23%. That has an impact on the injection cycle time of 16%. So, and reduce on warpage on 2.5%. It makes the difference when we are talking about serious production, of course. When we are talking about 1 million cycles, injection cycles, it could make a real cost benefit and impact on the profits, I would say, and the productivity for sure. And these are some examples of our jobs, build jobs that have, like you can see, it's a build plate of 500 millimeters square. And here you have some example of the cooling channels of some of the parts that are on this build plate. We can have all kinds of shapes according to the needs, almost like this on the cooling channels. We can have 1, 2 parallel cooling strategies or serials cooling. Here we have a core, a real core insert. This is around almost 300 millimeters tall part, around that. And you can see the cooling on the left, the cooling channels that are inside this part, and this part, it's high gloss finishing. So it's a mirror-like surface after the finish. And on the right, you have the printed part after as printed, I would say. These are a few more build jobs, as printed versions. Okay. All on a build plate from the 500. But it's like you could see, it's possible to do small parts, it's possible to do big parts, it's possible to do tall parts. So we can go inside this build job as the needs. And this is another interesting part. This was one of the most parts that has around 8 meters of cooling channels, a little bit more, but it really makes the difference. This part is quite interesting because it's a plastic part that could not be achieved. It was not possible to achieve with the traditional insert, we would say, because we could not have even stability during the injection process. It was a massive plastic part that was really making the difference using the conformal cooling channels. We were able to reduce cycle time, and we were even able to have stability along the process. And it makes a real difference on the production, I would say. This is another example. Okay. A few more. Small pipes, bigger pipes, according to the needs, according to the regions. That's a little bit of the strategies that we can go. And from my side, that's all, and I hope that you like it. Anything else? Feel free to contact.
Okay, thank you, Luis. Thank you, Luis. Very good presentation. So I will maybe leave the questions to the end, so you can use the chat to place some questions if you wish. But probably I'll leave the questions or the answering to those questions to the end of the session. Okay. Now I'm going to invite everyone to listen to Professor Nelson, if Nelson wants to start his presentation. Let me just see if that's possible.
Hello?
Hi, Nelson.
Fabio, can you hear me?
Yes, I can hear you. You can start sharing your screen if possible.
Yes, Fabio?
Yes.
Can you hear me?
Yes, I can hear you. I would ask you to share the screen. So.
Okay. I can start sharing my screen.
Okay. Okay.
Okay, here you go.
Okay.
So I'm happy to be here with a new concept of seminar. So we are having a joint seminar between Dornbin and Leiria. So maybe if I can turn on my camera also. Yes. Yep, you can see me. Good. Let me just give a quick survey about the audience that we have here. Is it? Not sure if it is visible. Oh, we don't see it there. But okay, so we have. Yeah, maybe you can also make the people side.
I think this is not possible because I'm a guest.
Oh, okay, okay.
Yeah. As a guest, you don't have access to the pictures.
Okay, okay. Never mind. So it was just presenting, and let us continue because we have to keep on time. So my part of the talk will concern an alternative approach. So in the development, in our development of software at CDRSP, we have considered solving the problem for deliverable, but we have observed that there is an alternative approach which we have been developing it on a sidetrack, which I'm now happy to share with you. We don't have results to present, but we have ideas, and so it's what I will share. It's about the ideas. So most think, or let me start with the basics. Let us talk about planar figures or planar geometry. Okay, we have an origin, we have scaling and rotation. So in order to fix a figure, we should settle an origin, and then we can rotate and scale. However, our observation in tackle the problem of conformal cooling channels is the observation that we can move out from the extrinsic geometry to an intrinsic geometry. So that extrinsic geometry, you would have coordinates for each point on the plane or on the space. Whereas intrinsic geometry, you don't really give coordinates for the points. You say how they are connected with respect to each other. So you say how much you want a certain edge to measure and how much an angle between an edge and its follower. And that's how you determine the intrinsic geometry. So what is the advantage? In this case, the shape is independent of origin, so you can place it whenever you want, and is independent of rotation and scaling, because also these measures are kind of relative to the unit measure that you are considering. Okay, so this and it even goes to so intrinsic geometry is about angles and distances, and it shows that the basic tools of intersections, orbits, offsets, etc., they are easier to implement in this type of language, and it even goes. I'll briefly mention it afterwards, to non-planar surfaces, but basically we'll talk about planar geometry here. So modeling this notion as a mathematical tool, we get a structure which we call a link. It consists of a set of indexes, so as many as the edges that you are considering, but it's just indexes. A transition map saying that to each edge, what is its following edge in the contour, its oriented contour. And a geometrical realization map, which actually gives the geometry or the coordinates to each starting point. So it is interpreted like this. So an element, an abstract element in the set of indexes, say A, which can be number 1, 2, 3, etc., is interpreted as an arrow starting at G of A and ending at G of phi of A. So that's how the whole structure is connected. And as you see, it forms this sequence of lines or edges, but it's in an abstract sense. So it's just after being, so it can be interpreted as this, but it's an abstract structure. And then we can perform mathematical tricks on it. So we can kind of take the first differential, let us say, with this formula, and this becomes independent of the origin. And we can take the second differential, let's say, it's in some sense, because it's not differential in the sense of classical differential analysis, because it's discrete, so it's just indexes, but it's the same intuition in some sense. So this second differential is now independent of scaling and rotation. That's why it becomes intrinsic. So that having only this second differential operator, we can recover the original geometry up to two constants. So it's like you differentiate twice and then you integrate and you get two constants of integration. And these two constants are, so the formula is a discrete formula. There's no integrals here, right? It's just sums and products because it's always finite. And so the formula is like this. And you see this constant is a complex number, gives you the origin of the region that you are considering. And the second constant is also a complex number, which has a magnitude and an angle. And this is what makes the scaling. So the scale is the magnitude and the angle is rotation. And so it's how you get intrinsic geometry in this shape. Now, this basic concept is actually the base of what we call the universal printer, because the universal printer is built up of these kind of structures. So we'll have what we call a mother curve, which is on space. Actually, it needs to be with quaternions because there is a twist on, so a vector has the possibility to twist, so quaternions are needed to really encode this. But it's similar to what before, except that instead of the complex plane, we have quaternions. But you see, we also have the transition map and the realization map. And what we have further now is an indexing family of planar curves. So to each index, we associate a planar curve. And then what is interpretation? So the interpretation is this draw that I tried to make here. And so there's still the mother curve that you see here happening, but in each point, we have a planar region. And that's how the printing process will evolve, okay? Then there is a non-trivial interpolation process between the cross-section on one point and the cross-section on another point. This interpolation process is somehow automatic, so we don't need to have information to determine it, but there are some guidelines because there is no unique solution for this problem. And I will show you some examples. So so here you see, suppose we have a planar curve with these three circles and another one with two. So how to interpolate? There are many solutions. In general, we could say that, okay, the interpolated surface from one layer to the next layer is this one, but it could also be like this, or it could be like this. So there are several options, which means that there is a little bit of information which is needed to perform the interpolation process. But apart from that, it's very simple in terms of complexity of data. So there is no much data which has to be stored in order to reconstruct the shape. And so in this light, I would just like to share three examples. So suppose we want to print a planet. All right, so this is a universal printer, so you can print everything. But maybe a planet is too much, so let's just print a moon. And okay, let us see how the structure would adapt to different printing strategies. So it's like the geometry is the same. It's always a sphere, let us say, but it's not just a sphere. In this concept, the geometry is decomposed into the way it will be printed. All right. So in conventional 3D printing, you would say, okay, the object to be printed is a sphere. But in here, this is not enough information. So what we have is, okay, let us say it will be printed layer by layer conventionally. In that case, we have a mother curve, which is like the z-axis, so sequences of vertical arrows. And at each arrow, we'll have the basic shape, which is a circle, and then is scaled. In this case, the origin is always the same, but it will be scaled. Bigger and smaller, that's how we get the sphere. Now, we could also print it as an orange slice, the slices of an orange. For that case, the mother curve is different. So the mother curve would be this equatorial line of segments, and the basic shape is like a half disc. And so that you would plug half discs and interpolating. In this case, interpolation is trivial because they are all constant. But each interpolation it would be what makes each slice of the orange, and then the printing is performed this way. Well, we could also consider a ball of yarn. I actually had to look at how to translate, because in Portuguese, novelo de lã. And so in this case, the mother curve is the real line of the yarn. And so it's kind of everything is encoded into the mother curve, so that the basic, in this case, the basic shape is just the shape of the extruder head, which can be a box, a circle, whatever. And by the way, in the other two cases, we would have to have an infill for the region. So say that's why offsets are involved. So in this case, I added here, think of electrospinning, because it's somehow similar to the electrospinning process. It would create a ball of yarn. And you see these three different ways of printing the same object, because geometrically it's just a sphere. But in this slide, with these tools, we have actually a more fine control, which is somehow telling how it will be printed. And of course, if the printer doesn't have the possibility to adapt to the way it has been designed, you can always simulate. So because we could also print this orange slice layer by layer, because you could decompose it further, and always a surface with intrinsic interior geometry can always be printed in somewhere other ways. All right, just very quickly to finish, this can be generalized to non-planar situations, so that the slices are not necessarily planar. And in this case, we would have the same approach. So each layer is now non-planar, but we still have the regions and has to be interpolated. And that's how non-planar intrinsic geometry appears. So if you have, say, a triangle with sides 1, you expect, and it's an equilateral triangle, if it is planar, you expect that the inner triangles up to pi, so it's pi thirds. But if you say, no, the inner angles are not pi thirds, are rectangles, right? So orthogonal angles. So suppose this is New York, this is Lisbon, and this is somewhere north of New York and Lisbon. And it will inevitably become a spherical surface. So if you force the intrinsic geometry to say my distances are 1, 1, and 1, and the interior angles are pi over 2 in each case, this is not possible to be planar, and this information alone would make the surface spherical. Okay, so there is no need to specify the curvature of the plane, the non-planar surface, because the intrinsic geometry automatically encodes for that. And so just to finish, I would also say that, so let us see an example of a dummy, in which case we see that the mother curve can be more complex. So in this case, we would have, and actually I've labeled it from 1 to 7 in the way it would be printed. It would be reasonable to print it. So let's say first we would print this leg, then we would print this leg, and then the body, and then the head, and then say this arm, and then this arm. So this would be the mother curve. you see the only thing that needs to be taken into account is that from each vertex there is exactly one arrow that leaves. Many arrows can enter, but exactly one arrow can leave, so that we have the concept of a function. And so in this case, let's use the basic shape of a circle, and you see the interpolation process happening. So in here we will have this. In this junction, we will have the usual truncation of 3 bodies into one. And what is more importantly, and I would finish with this observation, is that how can we apply this to conformal channels? Now think of this part of the belly as you want to simulate the heart and the lungs and the interior shape of a human body. And the interpolation process once again happens here. So if you say the cross section on the top is of this shape, the cross section on the bottom is of this shape, and with enough information to make the interpolation process, it will generate something like this. But this is exactly what can be applied for the conformal channels, because we can simulate decompose the part to be generated as channels, has layer by layer manufacturing, which is the way it will be printed in an SLM process. And this is what I wanted to say. So now I suppose we have still some time to say, I would say, Fabio, how much time do we have for discussion? Because we have to end up at 10, and I would also have to discuss here with the team here. So I would say I could answer 1 or 2 minutes quick questions from this.
Thank you, Nelson. We have some minutes for questions. Again, I would say that anyone who wants to place questions to Nelson or to Luis should use the chat to place those questions. So thank you, Nelson. Before going into, while people may think about the questions they want to make, thank you, Nelson, for the presentation. Thank you also, Luis. I think presentations are different but complementary so to each other. And no, I don't think we have questions.
But thank you.
Thank you, Nelson. I don't know if Luis wants to make some comments, some finalizing remarks, maybe.
Yeah, just to say that conformal cooling channels design, it's a real challenge, and from the perspective that I have seen from Nelson, it's real an headache. Every day it's a challenge to design them on the CAD systems, but yeah, it will improve a lot if we can design them more easier.
Yeah,
from my side,
if there was
the right tools.
An automatic and rules to design it automatically, it would be probably well, and I guess the optimization that you could achieve in cooling or warming, whatever, could be higher.
Yeah, at least easier.
At least easier.
Okay.
Okay. So no, I don't think we have questions. So okay, so maybe we'll end the session here. Once more, Luis, thank you very much for your presentation. Nelson, also thank you for the presentation. And as you know, this webinar will be then available on the ADDITOOL website for public viewing. Okay, so thank you all for coming. See you.